Alright then, hello everyone, and in today's lecture we're going to be talking about sequential logic. So in this lecture, the introduction, the output of a sequential circuit depends not only on the current inputs, but also on the past sequence of inputs. This implies that sequential circuits have memory elements, allowing them to store information about previous states. They are the building blocks for memory counters in state machines. The key characteristic of sequential logic is the presence of feedback paths, where the output of a logic gate feeds back into its input, allowing the circuit to remember its previous state. So in this lecture, we're going to talk about S-R Latches, D-Latches, D flip-flops, Mealy Moore State Machines, counters, and shift registers. In an S-R latch, or a set-reset latch, the S-R latch is one of the most fundamental memory elements. It can store a single bit of information. So this is the truth table. SR, Q, and Q bar, which represents the state. So when we set S equal to 1 and R equal to 0, we force Q to 1 and Q bar to 0. When we reset, forces Q to 0 and Q bar to 1. Hold. The latch maintains its previous state, and this is the forbidden state. And both Q and Q bar try to go to 0, which violates the fundamental property of the latch, where Q and Q bar should always be complements. If inputs return to S equals 0, R equals 0 from the state, the next state is unpredictable. And this is how we make an S-R latch with NAND gates and NOR gates. A data latch, or D-latch. The D-latch is an improvement over the S-R latch, specifically designed to eliminate the invalid state and provide a more controlled way to store data. It includes a clock input. So when the clock is low, the latch holds its current state, regardless of the D input. When the clock is high, the output Q follows the input D. Whatever the value D is transferred on to Q. This is why it's called a transparent latch. The D-latch solves the S-R latch invalid state by ensuring that S-R inputs to the internal S-R latch are never simultaneously active. And this is what a D-latch looks like, with some NAND gates attached in this way. A D flip-flop. While latches are level triggered, output changes as long as the enable signal is active. Flip-flops are edge triggered. This means their output changes only at a specific transition of a clock signal, either the rising edge or the falling edge. D flip-flops are the most common due to their simplicity and versatility. So this is what a D flip-flop looks like. So on the rising edge of the clock, when D is 0, Q is 0. On the rising edge of the clock, if D is 1, Q is 1. And on the falling edge of the clock, represented by this down arrow, doesn't matter what D is, and Q will just be the previous Q. So explanation, the output Q only updates to the value of D at the precise moment the clock signal transitions from low to high. At all other times when clock is low, high, or on a falling edge, the output of Q holds its previous value, regardless of changes in D. A D flip-flop. So this is what it looks like. A common way to implement an edge-triggered flip-flop is using a master-slave configuration, where two latches are connected in series. The master latch is enabled on one phase of the clock, and the slave latch is enabled on the opposite phase. This ensures that the output only changes once per clock cycle. Mealy Moore machines, or finite state machines. Sequential logic circuits often implement finite state machines, or FSMs, which are mathematical models of computation used to design systems that transition between a finite number of states. Components of an FSM. States, a finite set of possible configurations the systems can be in. Input, signals that cause a state transition. Output, signals produced by the system. And transitions, rules that define how the system moves from one state to another based on inputs. A Mealy machine. In a Mealy machine, the output depends on both the current state and the current input. Outputs are associated with the transition between the states. Outputs can change immediately when inputs change, even within a state. Generally requires fewer states in a Moore machine for the same functionality. So here's the initial state. According to this truth table, when the input and output is 0, we go to state 0. But while the input and output is 0, we stay in state 0. If the input and output changes to 1, we go to S1. Similarly, if we're in the initial state and the input is 1 and the output is 0, we go into state 1. A Moore machine. In a Moore machine, the output depends only on the current state. Characteristics. Outputs are associated with the state themselves. Outputs are stable and only change when the state changes, typically after a clock edge. Outputs are synchronous with the clock. So if we're in state 0 and we're inputting 0, the output will be 0. If we input 1, we transition to state 1, and the output is 0. And while we input 1, we stay in state 1. If we input a 0, go over to state 2, and we output 0. If we input a 0, we go back to state 0. In state 2, if we input a 1, we go to state 3, and we output a 1. Counters. Counters are special types of sequential circuits that can count the number of clock pulses applied to them. They are widely used in digital systems for timing, frequency division, and sequential operations. Asynchronous ripple counters. Flip-flops are cascaded, and the output of one flip-flop serves as the clock input for the next. Each flip-flop changes state at a different time, leading to a ripple effect as the clock signal propagates through the chain. It's simple to design, but they suffer from propagation delay, limiting the maximum operating frequency. Synchronous counters. All flip-flops are clocked simultaneously by a common clock signal. Logic gates are used to determine when each flip-flop should toggle based on the current state of the counter. It eliminates propagation delay issues, allowing for higher operating frequencies. So here's an example of an asynchronous up counter. The clock input is applied to the first flip-flop or least significant bit. The output of the first flip-flop clocks the second, and so on. Each flip-flop divides its input clock frequency by 2. So in this diagram, you can see the output of one flip-flop will propagate through each flip-flop. And here's a logic table. So as you can see, it counts all the way up to 7, and then it will restart. A synchronous up counter. For this flip-flop, it toggles on every clock pulse. Its T input is always 1. The next flip-flop toggles only when the first flip-flop output is 1. Its T input is Q0. FF2, this flip-flop, toggles only when Q1 and Q2 are both 1, which is from this AND gate. Its T input is Q0 and Q1. This design ensures that all flip-flops change state simultaneously, making the counter faster and more reliable. Shift registers. Shift registers are sequential logic circuits used for storing and shifting binary data. They consist of a series of flip-flops, typically D flip-flops, connected in a chain, where the output of one flip-flop is connected to the input of the next. On each clock pulse, the data stored in each flip-flop changes to the adjacent flip-flop. New data can be loaded in, existing data can be shifted out. So there are 4 types of shift registers. A serial in, serial out, where data is loaded bit by bit serially and data is read out bit by bit serially. In serial in, parallel out, data is loaded in bit by bit serially, and once all the bits are loaded, they are available simultaneously at the parallel out bits, useful for converting serial data to parallel data. Parallel in, serial out. Data is loaded simultaneously into all flip-flops. Data is then shifted out bit by bit serially, and useful for converting parallel data to serial data. And finally, a parallel in, parallel out. Data is loaded simultaneously into flip-flops, and data is available simultaneously at the parallel outputs, primarily used for temporary storage or as a buffer. So this is an example of a serial in, serial out register. So as you can see, the serial input is fed in. On each clock cycle, the input propagates through each flip-flop and comes out on the other end. This is a serial in, parallel out. So the data is fed in serially and propagates through each flip-flop, and once it's loaded in, is able to be read out in a parallel fashion like this. A parallel in, shift out register. So the data is fed into the flip-flops in a parallel sequence, and then it is shifted out with the clock. And finally, a parallel in, parallel out register. So the data is fed in parallel, and on the next clock cycle it is shifted out in parallel. So that concludes this lecture. This is the end of the video series, but I do want to make one more video where I go through all the concepts we covered with more examples. Thank you very much for watching.